Thank you very much for coming here today. Just a quick introduction from my part, Valeo. For those who don't know, we are an automotive supplier. The company is originally from France, but it's a global company, over 100,000 employees globally. We are here today to discuss the topic of the use of artificial intelligence for development of autonomous driving cars. For that, we have the best from Valeo here on site, basically. So to say, the first presentation will come from Mathieu Court. Mathieu Court is professor of computer science at the Sorbonne University, and as well partly cooperating with Valeo AI. Valeo AI is a branch of Valeo, so to say, that was established last year, exactly 1 year ago, and is steadily growing ever since. The Valeo AI is very crucial for the use of artificial intelligence in the systems of Valeo, of the autonomous driving systems that we develop as well here from Prague. In Prague, we have a big R&D center, around 700 people. Otherwise, the company in the Czech Republic has around 5,000 employees, even in the manufacturing facilities. And that's basically it from my side. So I will pass the word to Mathieu that will present how to design deep architectures for visual question answering. Yeah. So thank you very much for coming, and allow me to welcome Mathieu on stage. Yeah.
Thank you very much for this very nice introduction. So it's my pleasure to be here today. So okay, as certainly you see here, so I'm professor at Sorbonne and also part-time at Valeo AI. So the talk is not straight related to something that we can get tomorrow in an autonomous car, but let's say that it's more general things about how we can do some reasoning, I would say, inside into the deep learning. All right, okay, also AI reasoning and things like that. And there are not, I mean, like there are some ways, of course, to put that also into the car. And typically, I would say that the interaction, machine and human interaction, and talking and explaining decision and things like that is really, I mean, it's something that we have to think about when we conceive today somehow some autonomous or semi-autonomous car. All right. And typically, I mean, this has been done with two of my PhD students, and one is ending his PhD and will be part of, hired by Valeo AI next month, and we try to really develop these kind of things for driving, for autonomous driving. Okay. So typically, what is the kind of visual question answering? This is the old task of question answering about textual things plus a question that we can reconsider with the visual information by having like a visual data plus one question. And the thing is asking the machine to be able to derive, so to compute, I would say, so somehow some deep learning to compute a relevant answer thanks to that question from a human typically, and having like additionally somehow some visual information. Okay, so it's a quite recent task in computer vision, but it's excited a lot of people on that. Why? From the community. Why? Because it's a very nice playground to see how we can mix typically different type of information. In that case, is one question, so it's something like his textual things, natural language on one side, and of course somehow some visual information on the other side. And we have to merge them together in order to be able to give the right answer. All right, so we try, of course, to learn some systems, so to have like some machine learning to do that. And typically, I mean, the branch of deep learning is the one that I'm going to explain now. All right, and this is really, I mean, like this kind of task is really, I mean, seen as the first step to go further on human-machine interaction, right? All right. All right. So let me first give like very short overview of how we can mix together two different kind of sensor that can be, for instance, here the text and the image, and how we can learn this kind of embedding and things like that. And after I will be able to go more in detail into the VQA framework. So at the age, of course, of deep learning, the way that people recently designed this kind of task is really, I mean, like having a big deep to embed one image, or the output of one image, thanks to, let's say, a convnet, a neural net, a deep convnet, into one space, and in the same space we also are able to embed, thanks also to somehow some recurrent neural net here, a sentence or whatever, a word or a piece of sentence, or a sentence or a paragraph, or even a text, okay, some from a text, to be able also to compute and to find one point, okay. And so the main challenge is to put them together, is that to have this kind of common space. So what does it mean? It means that if I consider here one distance, as we are used to, I mean, that can be a Euclidean distance, I'm waiting to have like this kind of behavior. I will come back to the big picture after, but if this space is really semantically useful, so I can have, like, let's say, an embedding of a sentence, or let's say a cat on the sofa, somewhere in that space, and close to that sentence I can find some images. Okay, so this is the mixing that, of course, makes sense or are relevant with this kind of I would say caption, or let's say query, if it's a query, and this is the answer of that. Okay, and that can be, of course, in both ways. So the idea is that if I of course I consider one image somewhere, and I ask for having like the text that may give the shortest, I mean, distance with this image, will make sense with that image, right? Okay, so this is really, I mean, like the goal that we want to do is to define these two kind of deep architecture on both ways, in order to have after this very nice semantic distance that, of course, allow us to do retrieval. Okay, so we can do multimodal retrieval. I give you a new image, I go through that space, I'm looking for several captions that I have around already embedded in my data set, and then I can propose to the user the most relevant caption that give me a way to do some captioning, okay, thanks to data set of caption already embedded into that kind of system. All right. Of course, if you are able to reverse this step, okay, so if you are able to produce, so that means to generate from this space, that is conceptual space, you are able to generate things over the text, so you are able to generate caption, then that means that from one image, you are able to do caption generation, right? And of course, on the other side, I mean, that's if you are able from an abstract space to produce one image, so if you are able to come from that space, and you have the way to compute or to design a function from going on this way. So from this abstract space to that image, you are doing image generation in that case. Okay, so all these kind of techniques are related to the typically to the GAN approaches, right? And then, so that means that from one text, you are able to generate one image in that, right? So this is more or less the big picture for this kind of space. So that means what you need, of course, is to design, okay, both architecture, all right? And as it is big architecture with many parameters, okay, you also need to learn them, right? So if I try to instantiate that, so just see this picture, okay? Here from one image, I go through a big dip, and okay, at the end of the day, I'm able to produce one vector. So for one image, I go through, let's say, your favorite deep net that have been pre-trained for something. So that can have many layers. For instance, here the ResNet may have 152 layers typically that produce some kind of feature, okay, still with spatial information, and you can go through a new layer here and then to pull and then after to project to this new space. Okay, this is the kind of thing that we do love for image representation on one side, and for the textual representation on the other side. You still need to have like this kind of word embedding. Okay, for each word you need to project them into continuous space. And from that embedding, you are able to go through the recurrent neural net in order to represent in one vector the whole sentence. Okay, and since you are there, okay, actually you need to align them as much as possible. So what does it mean? It means that you need to learn all these parameters in order to do that. If you consider, I mean, like one image, a relevant pair, so one image plus its caption, okay, you should have 2 points there that should be very close. Okay, so it can be expressed as a distance, okay, minimizing the distance here between relevant pairs, or of course maximizing somehow some dot product in that space. Okay. And then, so that means you need to really, I mean, like fit and fix all the parameters in order to do that. So in order to do that, whatever the kind of relevant pair I propose to you, I should have here 2 points that are as close as possible together. Okay. All right, and as we have millions of parameters here, okay, we need to learn them. Okay, so they are one of the most important questions in that case is how we can define the learning scheme and where typically how we can find data, how we can collect data, how we can annotate data, and it's always, I mean, a very big problem for machine learning guys. Okay. There is somehow there are, I mean, sometimes, and this is good news, I mean, you can get some data for free, or it's free. For instance, if you are looking for recipes on the internet, you have plenty of websites that already propose some aligned data. Why? Because you have a lot of multimodal data that are coming and are ready and already aligned on the internet that tell you on one side the textual description typically, and on the other side the picture of the recipe. Okay, so in that case, and we have millions of that like that. I mean, one of our colleagues from MIT did some big collection of these kind of things. Okay, and then so that means you can learn because you have 1 million of pair of documents, texture plus images already aligned for you. Okay. All right, and we have a demo to do that. Okay, we can play with that after after the different talk if you want. Okay, but basically, so once you learn your system here, you can test your system, and typically you can test by doing some retrieval, cross-modal retrieval, and it's what you see here for this query. Okay, so it's a new data set or a new part of the data set that we call the test set. And you see, I mean, like the most relevant example in that case. So let's say the top 5 images closest to this textual embeddings. Okay, the same for that. And of course, we can reverse and put one question, one image, and asking for the best sentences corresponding to that image. Okay, so one step further, it's what we do propose with actually with Patrick and another PhD. I mean, like last year, is also to have somehow a way to localize the text into the image. Okay, so once you have this kind of very nice alignment, you can also back propagate the information into the image, into in the way that, for instance, if I embed two glasses, I go into that space, I see the image, okay, and I go back into the image, trying to find where I can find the most probable region where I can find this this text to information. Okay, and so if for the same image I ask for two glasses, this is a heat map telling me that certainly two glasses are located here. Okay, but if I ask for a bottle of wine in the same image, okay, I will be able to localize some other parts of the image that is better corresponding to the bottom, and it can be the same for the strawberries or other things. Okay. And this kind of information, how to localize different textual parts and so on into the image, may be also very important for VQ. Okay, so that's why I was also taking some time to explain how we can localize textual information into the big image. Okay. But this is the basic thing, how we can align, how we can at least mix in a very, I mean, let's say efficient, but also a very basic way, how we can put together image and text. Okay. So if there is no question, I'm going to now to go into the visual question answering, okay, task more in detail. Right? Okay. So I keep the same idea of having this kind of course, alignment, or at least mixing now. It's no more alignment. I need to mix them together. Why? Because in this kind of multimodal space, I want to have like somehow some merging from the color corresponding to that. I mean, for this visual information, and being able now to give the right answer. So you can see the problem as a little bit different because we need to merge them together into one point, okay? In order to be able to find somehow some answer that could be like natural text that should be close to this point, right? So when people start with that from computer vision community, we do like to have like benchmark and try different method and baseline and so on. So the first thing that we do is that we try to collect data and to do things. So this is typically example that you can find about this first data set and after another kind of data set, and this one was the BQAV1, and I will show other example. So what people collect, and sometimes doing manually and sometimes partially automatically, depending on other kind of things, while producing some question, okay, that can be difficult, of course, to answer for human and then after for computer, okay. And the basic idea in that case is to have like, okay, for one image and one question, the right answer, and for the training, you can imagine that we have this kind of triplet of images. Okay. All right. So, I mean, it's not an easy task, and we can see that in two kind of difficulties. Of course, if I only change one small things into my question, that may have a big impact into the way that I need to answer to that question. Okay. And on the other way, I can show you two images that seems quite similar in terms of semantics. There are two people, they are young, they are smiling, they are doing like that, okay? But with the same question, we ask the system to be able to answer completely differently, okay, in that case. All right. So that's why, of course, this kind of techniques, we really ask to have like a very good representation on both sides. So that means for your images, okay, you really need to take the kind of big deep convnet that I showed you before for the alignment, because you need to have like a very powerful representation on the image side, okay. And of course, this is the same for the question. You have this kind of, as I showed you before, this kind of just unfold the RNN here. But you also need to have this kind of LSTM, GRU, whatever you want to really represent as best as possible your question into and to embed that into a big vector also. Okay, and then after we need to mix them together to answer to the question. Right. So first point, very easy, is that the way that we represent the answer in this kind of problem, okay, we simplify the thing. I'm not going into the detail of that, but just saying that, okay, from one image to another, for the training set, we collect all the different answers, and we say, okay, I just keep the, let's say, 3,000 of most frequent answer that I get into this data set, and I cut, and I don't no more consider the other one. Okay, and by this way, of course, I really transform my output as a classification problem. Okay, because I just keep the 3,000 most frequent answer, and it's over, right? So I'm just skipping that explains this kind of thing. So my problem, my VQA problem, that is really, from one image having this kind of very nice deep representation, the same for the question. Then I need to mix them together and to be able to produce one out of, let's say, 3,000 of classes, okay, and to produce and then one answer, okay, in these classes. All right. So so we are going to just, I'm going to mention two steps: the fusion and the reasoning, that are the most important way to integrate and to mix the information into both media. So the fusion, that is certainly, yeah, okay. Usually, like, people do not consider carefully this step, but it has a great impact the way that you do this kind of thing. Okay, so the fusion we consider here, okay, is coming after your deep representation. So you have one vector that characterizes your question, okay, and you have one vector characterizing your visual information. Okay, then you need to mix them, to merge them together. So the output of this merging is again one vector, okay? And you can continue in a deep, or at least one step here, and to produce, okay, the output vector, right? And so there are many ways to merge. Of course, the most simpler way is just to concatenate both vector and to put some linear projection, or to put some deep into that. But what we really notice into the community is that the best way to do that is to consider, let's say, the element-wise product. So here, that means that you produce the vector by multiplying, component by component, each of them, right? And if you see that in a more general thing, this is really, like what people call the bilinear transformation. So this is, sorry for the math here, I will skip the next slide, don't worry, but okay, this is just a way to put them together in a bilinear way. So I multiply each component of the visual information with each component of the textual information that can be different. And of course, I have like a weighted coefficient, scalar coefficient for that. If you do that for any kind of combination that you can have in between, all right, you will obtain one scalar here, okay? And you can, of course, define many ways to combine them, and so many kind of weights that you consider. And then, so if they are different, you can really, like, get a vector as an output of these things, okay? So this is the big picture, right, of that. And this is really, very well known by signal processing community for, I would say, 30 years, perhaps. And we do have many, let's say, framework to analyze these kind of things and to do some kind of decomposition. And so it's what we can do in this kind of thing for, so I'm not going to develop, but so to have this kind of big tensor decomposing in something like quite sparser in order to be able to computationally work with, right? Okay, so this is just a question of how we can decompose many things. So in between the different approaches, we can consider several schemes that do this thing. But my take-home message today is just, it's very important to consider this kind of bilinear combination, whatever the kind of bilinearity you consider. But there are, I mean, the most efficient methods at the moment, okay, state-of-the-art method to do that, okay? Yeah.
Just a quick question. How do you actually, how to rephrase it? How do you make sure that the vectors, the visual vectors, so the encoder for the visual vector and the encoder for the text information is giving you something that you can multiply together in some reasonable sense?
Okay. Yeah. So the point is that all this coefficient will be learned, right? So the idea is that we don't claim that this combination with that coefficient should be important, okay? We just say it's possible, okay? And after it's end-to-end learning, so we are going to see if the system discover some really powerful combinations, right? And so my answer is just, it's empirical. So I will define this kind of system. I will try to learn them, and I of course I compare with other, and I really notice. So if you see, well, it's just if you see on other kind of fusion, so this is really, I mean, like we just compare the one kind of fusion, a second one, a third one, etc. And with all this kind of tensor-based decomposition, okay, and systematically, I mean, like you have a game with, and so most of the techniques adopt this kind of bilinear decomposition for the association. Okay, so this is the first thing. And the second one is, this is very interesting, is that we can try, of course, to visualize. We can try to see what has been learned. And so after we can try, so, and this is typically, I mean, the first part of reasoning. So it's a good transition. Let's say, when we are talking about attentional reasoning, I'm going into like that, okay? So we can try to see where and how and which kind of tensor and multiplication and combination could be good, okay, and have been learned typically. And this is a way to monitor that, perhaps that type of color, I would say, if it's a big picture, combining with this kind of textual embedding, or I would say this kind of word, okay, should be considered as in a very multiplicative way, and with a big weight for that, okay. Right, and so it's a transition. So sorry to going fast, but we are no more. So yeah, 5 minutes from. Okay, so but this is typically the second part of my talk. So the first part and the take-home message is that the fusion-based techniques are very important for VQA, but not only. I mean, at least as soon as you need to merge two different sensors into a deep architecture, okay, you can of course consider having some kind of on each side deep layers. But when we try to make them, okay, there is a very efficient way to do that, is bilinear combinations, whatever the kind of tensor reduction that you consider. But the way of considering bilinear reduction, bilinear combination is, this is, I mean, a very efficient way at the moment. And then after, of course, you can continue by several layers again until the final answer. Okay. And okay, and this is very efficient for VQA. And the second point for VQA is that of course this is not finished after that. We also need to put somehow much more reasoning. Okay, so reasoning about question typically, and the first way to reason on that, because sometimes questions are very, I mean, like conceptual, and it's not easy just to say, okay, I have two vectors, I merge, and it's okay, I can find the right answer. So one way to put something more complex is to put some attentional process. So to say that perhaps the whole image is not relevant to answer to that question. Is it possible to help me to shortcut and not analyze all the visual part, but to be able to focus on really, the most relevant part? This is typically what we have here, okay? If we are able to produce this kind of thing, so thanks to that question, of course, not analyzing the whole image, but being able to say, okay, I'm defining an attentional process that tell me that thanks for that question on that image, certainly this part is more relevant for the answer, okay? I will do part of the job, right? And so how to do that, okay? Before I was considering only one vector here, okay? But I can, with ResNet and all this kind of deep structure, I can keep some spatial information into my representation here, okay? Having this kind of grid that tell me if this vector is represented this far, okay? And then I'm going to merge them now, all these different parts, so I can merge them together in order to produce this kind of attentional map, okay? So this part is really, coming from the beginning, just to be able to produce this kind of weighting, okay, region. And then I can reconsider the whole block instead of having only the classical vector as before. I can now consider a weighted vector that coming from the weight are coming from this, okay? You can imagine like exactly a binary thing is that I just remove, okay, the top of the image and I just consider the bottom. So I just keep the representation of that and I pull them and I just summing them together, okay? And after is the same thing as I presented before, right? So this is typically what we did in this kind of system. It's also still end-to-end learning, right? And thanks to that, this is real example I show you is that if I try to visualize the kind of attentional process that I have for that question, as I mentioned, that attentional process, I would be able to learn thanks to the current interpretation I have. If I change the question, for instance, for the same image, I go through my process and I just visualize also the heat map. I will see that here, of course, this will be able to much more efficiently select the top of the image. That makes sense with, of course, with the question. Okay. So we can put, yes, many things all together. We can also say, okay, I'm not interested in having like the fixed grid, so I can consider this kind of bottom-up process with, but this is basically the same kind of thing that we can put all together. Okay. So that was for attentional. Still have 1 minute, I think. So we do also consider relational things. So relation is that if you have no more, like one grade or some kind of different region that makes sense for the question, okay, you can also consider some relation in between the different regions. Okay, so you can try to also infer that it could be interesting to have like some attentional process that take into account the relationship or the relation in between the different regions. Okay. All right, and finally one thing, and that I will finish on that, is really about this kind of sequential process that we can have to analyze the question in order to give the right answer. Typically, if the question is what are sitting in the basket on a bicycle, you have like, let's say, 3 bicycles here. Okay, so this kind of question should or can be at least split into several tasks. Okay, first find the bicycle. Okay, inside the image. Then find the one that has a basket. Okay. And then focus really on that basket and tell me what is in. Okay, so this kind of iteration that it's different than before because you need to finish the first step, and this is conditioning the second step, and the second step is conditioning the way that you are doing the first step. Okay, and this is what we see here in terms of attentional things also. So it's not the same kind of color, but you really understand is that The idea is that from the first step, we are able to focus on all the parts where we can see, so at least 2 bicycles when it works correctly. And after to find the one with the basket, and after to really focus on what is inside the basket. And from this answer that is depending on that one, okay, we are able to answer correctly to the question. Okay. So this is typically, I mean, like one thing that we put all together. So having this kind of attention process, putting the region together, having this kind of iterative scheme, and keeping all the things about the fusion, bilinear fusion into that we recently proposed, we will propose that on the next big computer vision conference on that. But let me just show on one example. So what we are able to produce and interpret, last slide. 2 slides of example. Okay, so you see, for instance, what game are they playing on the Wii? Okay. So they are playing, so this is a screen, so you certainly need, we can see very well, but we have a screen here, okay, with bowling, with boons and so on. And here we have one people and trying to do something with the device, the joystick, okay? And so you see that at the first step, we are really able to focus on these 2 parts, okay? So at least removing some part of the ground on the background. And then also to be able, after that step, to produce this second step, by much more focusing on some region on that, and typically to be able to produce and to focus on at least on the joystick and on the screen, okay? And also on the relationship between them, okay? All right, so you see different examples, and of course, there are some kind of bad cases. Okay? Yeah. All right. So it's, yeah, okay, I can stop on that, or I'm taking some question about this task. Thank you very much.
Are there any questions?
Yeah, I would have one. If you plan to extend the approach presently, which is by the way very nice, thanks for that. From classification problem to second generation, because currently you said that you are generating one answer that is picked from the most frequent one.
Yeah, sure. Yeah, so as soon as you are able, typically to have this kind of recurrent reasoning step, okay, as I presented at the last one. So this is really, I mean, the idea is that here you are producing the question. So and thanks to that question and the visual information, you do something. So you do part of the job, trying to analyze more or less what can be this kind of output, and then you come from this intermediate output with the same question, okay? You try to refine the question with this output to produce another output and so on. So the straight way to extend that with somehow visual interaction, okay, is to say that this answer or part that one, okay, is the first answer to the system, okay, and then the user seeing this answer may interact and ask for another thing, and thanks to this other thing, I mean, you can continue, but at least not with the same question, but with another question given by the user. So this is really, I mean, like easy to extend this kind of approach, okay, just having this kind of interactive sequential step here into visual dialogue.
Okay, if there are no other questions, thank you, Mathieu.
Thank you, sorry.
Delivering this presentation. And let's welcome the next speaker, Associate Professor from Czech Technical University, Mr. Tomáš Svoboda, Head of Department of Cyber.
Okay, so I'll probably slowly start. So thank you for inviting me and for introduction. So for those who forgot, my name is Tomáš Svoboda, and you know, I am the one who made the break possible. So I hope you appreciate it. And now you are in a good mood to start. So I'd like to thank my collaborators. Of course, this is definitely not only my work, and I also would like to thank the kind sponsorship of European Union through various projects which made the research work possible. When I was preparing the presentation, I was not really sure what would be the audience. So one question now, who knows what reinforcement learning is? Okay, quite a lot. It's about half and half. Okay. So those who just raise the hands, please forgive me this slow introduction. Then I will end up with the usual stuff with deep nets and so on, but I will start this kind of almost pre-deep net time. So what's our world? So our world is unknown, unstructured, and rough. So it's about driving. It's about driving the robot inside and back, if possible. The good thing is that we sort of have enough time. The robot is moving really slowly, but yeah, no map, no nothing. I mean, even there was a map before, probably it's no more valid anyway, like this after earthquake deployment in 2012, and the same for 2016 in Amatrice. Okay, so and what we are up to, actually the main goal of this project, which was called Trader, was to find a way how the robots, actually ground robots and the flying robots, can efficiently collaborate with the rescuers. Okay, so we collaborated with firefighter groups in the several European countries. The Italian guys were the most active and helping us, providing their facilities. So, and actually, I got the feeling with them, it's like a little bit similar like with the medical doctors. They like the support software and so on, but I often like to drive the robots by themselves. Okay, so they were not that excited about the autonomous driving as we were. They simply wanted to have efficient way how to use this robot, okay, for their work. Okay, so, but of course, one thing is driving robot somewhere, just go there and wait there, something, by clicking on some screen or using some gamepad or something. But the robot has a lot of degrees of freedom, so to control it fully, it's really difficult. I mean, for some of you who are much younger than me, it's probably not that difficult, but for me, definitely is. Okay, so yeah. So you can control many things, and for instance, okay, so this is more recent snapshot of what the firefighters are using. So imagine the firefighters sitting in a track, few tens of 100 meters from the disaster site, and yeah, they are driving the heterogeneous set of robots through some interface we developed. We were interested in the ground robots, and the robots is propelled by tracks, and to overcome obstacles, it has something we call flippers, which are those small pieces that can be tilted up and down independently. Okay. It has the usual sensor suite you would expect from the outdoor robot, so some depth sensing through LiDAR, the omnidirectional camera to see around, and some inside sensing providing information about the orientation of the robot in the terrain, accelerations, and so on. And okay, to drive it, of course, you have to specify where to drive, the driving vector. But in addition to that, in rough terrain, you need to specify the flipper angles, the stiffness, which is essentially how many current you put into the drives, just to, for instance, to make the suspensions like behavior of the flippers. And in addition to that, you can also control the differential brake, which is sometimes not always the good idea. So the differential brake allows the robot to move even the main track bodies independently, which actually at the very beginning sounded like a good idea, but it turned out to be not that useful in a very harsh terrain. Okay, so sometimes it's better to keep the differential brake locked. Okay, so a little bit introduction into the reinforcement learning for those who don't know. Okay, so this is a toy example I use for my teaching. So this is a grid work. Think about that the robot at the moment is here and doesn't know about the environment. So you see this, but the robot does not. Okay, and somewhere in the space there is a good ending and also bad ending. Like think about, okay, making the job finished and falling into the hole somewhere. And those positions represent the state of the robot, where the robot can be when driving inside. And those weird-looking numbers are saying what action essentially is the best. So here in the grid-like work, you have 4 possible actions, like moving up, right, or east, if you like, to south and to west. And obviously, when the robot has this kind of information, like about what action is the best in which state, then it's easy, right? When you start here, you just, okay, you have you can take this or this. These are equally good. So let's take this. Okay, 6 is better than those guys, and so and you easily end up with in the good solution. Okay, here if the robot is in this state, you probably going here is not a good idea because the price is very low, even negative. Okay, and in addition to this reward far away, there is some cost about for making the action. So in this world is very simplified. Just any action here in the world costs -1. It's like a penalty for dwelling in the grid, consuming energy, and so on. And in reinforcement learning, there are methods how to learn this, say this evaluation of the function of the actions from trials, from driving the robot in, collecting the data, or from simulator, as you will see later on. So I will show a few steps. Just once again, this is the bad ending, this is the good ending, but the robot doesn't know anything. Okay, so at the moment they are all zeros because it knows nothing about the whether this action is good or not. So it goes and it learns some values on the way. So some reinforcement learning algorithm is actually already running, and this just says that actually going here brought no real reward because there is nothing at the moment, and it just costs -1, and there is some learning parameter just saying that okay, this -1 will be made half because there is a learning rate 1/2. Okay, and you continue, and it is good. Okay, here the robot got to know that this is a good thing, so here is quite a high value, and you repeat. Here is quite easy for the robot because the robot is deterministic, so the robot always does what it's commanded to do, which is not always the case. And the algorithms work even for the not deterministic robot, as you can imagine. And okay, here you learn some values. You can turn those values into a policy. So policy, those small arrows. So whenever the robot happens to be in this state, the optimal policy or strategy, if you like, is going in this direction. Okay, and then you can perform the actions as the optimal policy it says. Okay. You know, so I really like teaching, so forgive me about this interruption. Okay, so what are the states in our case? So we use the proprioceptive measurements, you know, the roll of the robot, the pitch, the torques, essentially the current that's going to the engines, the velocity and acceleration, if you like. This is just a design choice. You can think about any other combinations if you like to. And of course, we want to use the information about the environment. So what you see here, it's looking, you are looking from the top. Here's the robot, and those colored values encode the height of the terrain. Okay, at the moment I don't know actually if the more pink the deeper or the higher, I don't know at the moment, but you can, during the years we use this elevation mapping in various forms, so we can think about any features you can compute out of it. You can even, and we did, use the values directly in some learning algorithms. Okay, at the very beginning of our work, you know, the firefighters wanted it, so we were a little bit in a hurry. So we simplified the thing a bit. So instead of controlling really all the things, which is quite a high-dimensional problem, which is actually one of the problem for reinforcement learning, how to find a policy when there are many dimensions, many things to control. So we made it discrete, and we say, okay, for traversing various obstacles, there are some good predefined positions of the flippers that allow, you know, going over the obstacle. So if you are going up and down the stairs, you typically need the flipper stretch in order to maximize the traction. When going in an easy terrain, you want to have the front flippers back just to allow the wide field of view for the sensory field, and so on. Okay. And the last item you need for the reinforcement learning are the rewards. Okay, so the reward value is something the robot is given just immediately after taking an action. Okay, so the robot is in a particular state, it performs some action, it's commanded to do, and it receives some reward for it. It can be either negative, like, okay, consuming energy, or it can be even positive, like, okay, the robot is accelerating, so probably the action was good because this is what we want, to have the robot driving over, right? And of course, you want to penalize some dangerous thing like higher acceleration, meaning that the robot is falling down and hitting some obstacle or something like that. And again, it's a design choice. And the goal of the reinforcement learning, a algorithm from that field, is to learn not the best rewards, the immediate rewards, but the sum of the all rewards. So sum means that you start in a particular state and you end up in a terminal state, or the episode is ended by someone else because it took too long. Okay, and you want to find such strategy that's essentially the function that tells you what to do in each state, that maximizes or minimizes, depending on the formulation, the total sum of rewards, the expected sum of rewards. And you can do some discounting, but that's not really important here at the moment. Okay, so that was the educative, or I hope it was a little bit educative beginning of the talk. And okay, so we did some training on, say, some characteristics objects, so characteristics obstacles, like the steps up and down. And we are thinking, okay, maybe we will be lucky and the real obstacles can be actually understood as a combination of say, standard obstacles. Okay, so this is where we're training the algorithms, and this is where we were testing or evaluating. Okay, so some comparison between the manual control and the automatic control. The automatic control does better almost everywhere, like preserving lower pitch and roll, being faster, and so on. With the only exception that it had to use more changes of the between the modes than the human operator, which is quite natural because, as I told you, changing the modes it's quite difficult. So, of course, if the human operator drives it, he or she changes the mode just only when it's really necessary. Okay, and this is just driving in the wood. So here in this case, the robot, the velocity vector is given manually by an operator, but the flippers are controlled automatically. Okay. And actually, it worked quite well, and yeah, can be successfully tested. But we were not happy. Yeah, the researchers are seldom happy. I mean, they always are trying to find the more and more difficulties, the more challenges. So one of the difficulty when deploying such kind of robot is that often there is a smoke, dust, and nasty things like that. Essentially, blocks the LiDAR sensing. So in a even quite modest smoke efficiently block the LiDAR, not speaking about the camera, of course. So sometimes the data is missing. So okay, not everything can be solved by machine learning. Okay, so okay, small part about without machine learning. So we said, okay, you know it. You woke up somewhere in the hotel where you've never been, and the light's not working, and you have to go somewhere in the night, right? So what do? You simply try to, okay, maybe not in the hotels, but I used to go to the mountains, to the mountains huts, and of course there are not that luxury at the standard hotels down in the city. So there are often problem how to find a way in the complete dark. So when we are using touch sensors to find a way and trying to avoid the stairs we saw yesterday. So we enrich the robot with the tactile sensing in the flippers, right? And the idea is, okay, let's use the flippers, to to sense the terrain and to find the shape of the terrain just from sensing. So okay, here there are four sensors, and here the fourth one somewhere here strike the most. Okay, so you might guess what's the terrain, and for various kinds of terrain profiles, you can get a different sensor profiles. Okay, so the good thing is that when driving with the firefighters and so on, so we had quite a lot of data how the robots were driven over various terrains. So we were able to learn some statistical model about the terrains. Okay, so that's Karel Zimmermann. He's a really good guy, very unselfish. No sacrifice, no victory. He's really capable of doing anything to get paper published. So this is just visualization of deep sampling that is trying to find an optimal, or not optimal. The final terrain profile is estimated as the mean of the GIPS samples. Okay. Okay, so the input is again the information about the robot, the sensor data from the type sensors, and the output. What we wanted is a terrain profile, which is here quite a simplified one. How it works, and again, we wanted to make even more interesting. Okay, so if there is no enough information about the terrain in front of the robot, so okay, we can use probably the touch sensor the arm as a type sensor, so it touches the terrain, and voila, we got a new measurement. So the estimation is much more precise than before, and the robot can proceed. Okay, and so to make it really safe, so here the robot will be performing safe blind traversal. So this is what the operator or the controller, say, can see. The robot is going fully autonomously, just moving a little bit forward, doing the sensing, estimating the profile, waiting for the allowance, for the clear run. If it receives, then it goes farther and so on. So it, yeah. So those are the flippers. This is what's blinking is the Bluetooth wireless mode. Of course, it's painfully slow, actually, but sometimes it's better to have it really slow than to have at least something, not to have a robot somewhere in the dust and lost for or waiting for before the dust cleans up. Okay, so to do all this, we improved. We contributed to the gazebo simulator with a new tracked model. There are many ways how to model the tracked robot, and we wanted some properties these standard models didn't have. So yeah, we designed a improved version of a tracked model. This is just the comparison with the existing model. So for the standard drive, it was usually okay, but when the robot started turning, going up and down, many of the existing models didn't work as we wanted. Okay, so that's all fine. Okay, learning in the simulator. So this is what you would like to have, right? A good simulator, then let the robot run and run and run. It's always good when you are leaving the work, you can hit the button and let the machine do the work, and then come in the morning and to see the algorithm is learned. It's always a good feeling. I'm always happy when I can give the work to the machine. So that's the idea. Okay. So but to have it successful, what's missing? Okay. So to do it, it's not, we need to build some, say, world by ourselves. And of course, we have to have some kind of simulation of the sensory field. Okay, and ideally as fast as possible, right? Because the reinforcement learning often needs really many trials to converge, if at all. So okay, we can do some geometry computation, but this is not the real world. I mean, also the automotive guys know it very well. So what we want, okay, so this is an example of a real data. It's not just the measurement of the LiDAR. What you see here is the result of an algorithm that does the elevation mapping. Okay, so it uses the depth measurement and create some local height map of the terrain. Okay, this is how we can simulate the same thing in the simulator, and this is where we want to be, right? So having this kind of input, then have some machine here that would convert those data into these. Okay, so we are not really simulating just the LiDAR sensor per se. We want to simulate the whole mapping. Again, it's design choice. I mean, you could also simulate just the LiDAR and then do the computation by some other means, but that was a design choice here. Okay, so the bad thing on it is that it can't be converted into standard supervised learning, right? Because you have the virtual data, say, and the real data from your experiments. Okay, but in a standard supervised learning, you have the direct correspondences, what's the simulated and what's the real one. This is something what we don't have, right? You can say, okay, those are the data for driving over pallet, and I can simulate the pallet driving over pallet in my world. Okay, this is sometimes possible, but in the real terrain is difficult. And of course, you have the timing issue. So driving over pallets can be different. Even if you drive over one pallet, you can drive faster, slower, and so on. So the word, it was already mentioned, the world of today is one of the words of today is the generative adversarial network, the GANs. And here is even cycle GANs because you don't have the direct correspondences. Okay, so I'll try to explain pictorially or maybe using this image. Okay, so you have a real data and you want to convert the real data to simulated like ones. Okay, so you have the simulated generator initiated by the real data, and you can also go back, right? If you put the generated data into the opposite generator, you end up, or you want to have this elevation map as close possible to this one, and the same for the opposite direction. Okay, so you have the simulated data, you are trying to make the real data out of it, and you are putting the sort of like the real data back into the generator to get the simulated data again, and you can measure the loss between this guy and this guy, and between this guy and this guy. Okay, right? I simplify it a bit. The specialists for GANs don't mind. Okay, and you know, it was uneasy to trying to explain it to you, and the actual learning is even more and more difficult, far more difficult. So it's I mean, the idea is nice but to make it really working, it's not that easy, and it needs some magic. This needs to us. Okay, this is maybe I skip. Okay, few words about the data. So the input is the elevation map, and again, it's design choice. I'm not sure if this was really the best idea, but okay, there are some missing data. Okay, so we split it. So this is the height map, and this is the say encoding map that says what data are probably wrong or missing and what's not. And this is adding the angle of the flippers, and I think this is the pitch angle adding to the generator. So this is the architecture of the generator, and the architecture is the same for making one path, so from real to the simulator, and from simulator back to the real. Okay, so and the idea is to learn it all together. So having the simulator, we can do some offline stuff like the planning, the optimal path using the rapidly exploring random trees. This generates some set of the trajectories, and we can use this optimally planned set of trajectories to learn a policy in a simulator. Okay. So then the policy is telling the simulator what action to take. And this runs for the whole loop. I probably show this scheme in the next slide. And to make this working well, we also learn the GANs to satisfy the quality criterion for the policy. So we are making the policy as best as possible and learning the GANs in the loop. Okay, so it starts with in the simulator, it gives you the planned policy. Then you do the supervised learning, so you are learning the policy, so knowing how to act in each state from the planned trajectories. You are doing this in the simulator, and sometimes, not of course, this path is much costlier than this one. Sometimes you also say, okay, maybe it's time to try on the real robot, and then the trajectories from the simulator and trajectories from the real platform goes to the cycle gun thing in order to learn the as good generator as possible, and it goes back and it repeats. Okay, so this is just how it might look like at the end. So there's some strange noise, but actually many real data look like that. And yeah, so the hope is that from this kind of data we can generate better policies. And that's going to end my talk. So okay, this is not. Okay. I thought this. Okay, it's also moving. Okay, so this is going over obstacle. This is just to give credit to Martin Petska, who is harming the robot in the water. And this is this invisible guy here is Valeo Kubelka, who is driving the robot somewhere in the windy night in the Italy. So thank you for the attention.
Thank you very much for the speech, but if there are any questions, now is the time to ask. And if there are no questions, then we will move to the next speaker, the last one of today, which is Patrick Perez. Patrick Perez is director of Valeo AI, so definitely the right person to speak about the use of AI in autonomous driving. Okay. Let's see if the technology works well, or we need another break.
Switching to HDMI. Let's see.
And we need to press.
I need to press something.
Yes, perfect. Oh. Okay.
Okay, thank you for the introduction and the invitation. So before I start, just wanted to make some comments. Yes, before I start. Just one comment about the two previous talks. So regarding the one of Mathieu, I think what you got a glimpse at is what is the current state of the art in modern AI in visual understanding. And for the researchers, it's really fantastic. We made really incredible progress in the past few years. But when you see the type of questions which are asked to the system, and when you think the type of analysis or the type of reasoning we do as human drivers when we drive a car, you can measure how much we have to continue work on these questions, and that's really I think we are just at the beginning of automated understanding of scenes, whether with images or radar or LiDAR, etc. It's definitely very challenging. And one can even argue that autonomous driving is probably one of the hardest, not only engineering problem, but also an even more artificial intelligence problem at all, because you have to understand, it's in the wild, it's very unpredictable. So you said unknown, rough, and unpredictable. Yes, that's very true for urban environments when you drive your car. It's of course, it's embedded system is very critical because there is a safety at stake. It's interacting with other robots of the same type, because an autonomous car is a robot, not quite the same as the one we saw before, and it does interact with other actors and agents which are basically human beings, which are called sometimes in our jargon vulnerable road users like cyclists, pedestrians, etc. So immensely difficult task. Okay. So whether it will happen in 5 years or 20 years, that's another debate. But you kind of get my feeling on these things. Regarding the presentation that we just saw, apart from the fact that some of the images reminds me of a very sad event which happened 2 days ago in Paris with the smoke and the flames, and it's really a heartbreaking day. There is something very interesting, and it helps for my talk. It will help me making it short, which is that there is a lot which is done on simulated data, and at some point you have to deploy your system on real data, and there is this gap that has to be somehow filled between the synthetic and the training data and the real data, and which is really the topic of this presentation on the domain adaptation. And I will, but I won't talk, I'm not going to talk about reinforcement learning and robotics. I will focus really on the visual perception, which is one part of the perception that you have to do in a safe driving car or even in an automated driving car. So there is this issue that at the moment the state of the art is based on, for perception, is based on deep learning. And even when you do reinforcement learning, there is usually somewhere a neural network. So deep learning is essentially artificial neural networks, very old ideas, and it's really state of the art on the task. We saw visual question answering, understanding scenes, etc. But the most of the power comes from what is called supervised learning. So you have to train your system with complete knowledge or with a large set of examples, which really shows the raw input and what should be the prediction of your system. So you really show complete examples for the task that you're interested in. So that's obviously powerful, but it comes with a caveat that you need to gather this data, this annotated data. So not only is it difficult to gather raw data at large, as we saw, because sometimes it's not even possible to deploy your robot in real or your car in real situations. And on top of that, and you need to cover all the possible scenarios or as much as possible. But for supervised training, on top of that, you need to provide the annotation, what is called also labeling. Okay. And labeling is really hell in the sense of it's very expensive, it's time consuming. I'm going to show examples, obviously. Sometimes it's not even possible. So let's take an example, which is really the one of the core tasks I will have in my talk, which is what is called semantic segmentation. So semantic segmentation is the task of associating to each pixel in a scene a class, a semantic class. So a street, pavement, tram, tree, constructions, poles, lamps, traffic lights, etc. So if you want to do that by hand, as you can imagine, on real images, it's a painstaking task, and it has to be done if you want to train your system for this task on real data. So what you see here are images from the cityscapes dataset, which is a very popular academic dataset for this task. Not only this task, but among others. And in this data set, there are 5,000 of these images. So 5,000 is a lot for the effort of annotation. It's pretty tiny considering the type of diversity that we want to cover. So this same data set comes with another set of images, like 20,000 of those, which are annotated this way, just because otherwise it doesn't scale in terms of manual work. And this is called raw annotation, or gross annotation. So this is what the type of things I'm talking about. And here it's humanly feasible. There are other tasks. Imagine that in addition to that, you want at the same time to estimate for each pixel what is the distance to the physical point in this pixel to the camera. It's called a depth map. So if you ask a human being to provide a depth map out of an image, it's just not possible. It's not okay. So to do that, of course, there are different ways. I'm going to mention them. And even if you are able to provide as many data sets as possible, to real or synthetic with annotation, in any case, there is such a diversity, so much unpredictability in the real world that there are things that we will not be able to see at training time, and somehow the system one day should be able to improvise, which is not so much the case so far. So just keywords here, and I'm not going to go through these things, but just to say that in the machine learning community and way before the deep learning era, there has been many ways to address or to complement this full supervised regime, which is very expensive and in a sense restricted because of that. And so there are a number of alternate supervisions, which allows one either to learn with less data or less annotation and maybe bigger data sets but with fewer labels, or no label at all. It's called unsupervised learning. All the way to what some things that we saw, which is to learn from synthetic data, and this kind of thing, or in any case, to learn from data which are not exactly the data that you will face at runtime. And this is a very important thing. It's called transfer learning in the most generic version. And I'm going to talk about a specific version of that, or variant of that, which is called domain adaptation, which is especially interesting when you do training on synthetic data. Transfer learning is when we train. So either you train on a given task and it turns out that it's not exactly the task you're interested in, but you can somehow reuse what you have learned at training time, or it's exactly the task that you know for sure that you want to address, but you train on a different type of data to some extent. So it's a different statistical distribution if you wish. And in this later case, this is what is called domain adaptation. So what is a bit funny here is that one can argue that there is a streetlight effect at work, which is I don't know if you know this thing, but you search for your key under the light, because this is where there is the light, but you lost your keys somewhere else in the dark street. It seems a bit silly, and this is what we do. Essentially, we learn something different. Okay. But of course, it's not so bizarre, because there is a lot of structure which is shared, and if not, then you are really back to the street light effect. So I'm going to focus now just for at high level on this very specific scenario where you train on data which have a different distribution. So again, it's called domain adaptation. Because there will be a training domain and a test domain, also called source and target domain. I'm going to skip that. So, so there is this idea that, as I said, that you're going to. All my examples are with images, but you can easily think in terms of other raw data, raw sensors, raw signals, sorry, and different tasks. So you can train, for instance, on clear time images because they have been recorded in California, and then you want to deploy somewhere else where there is snow, for instance. So because of this weather, there is a gap. Also, you might train at daytime and test or deploy also at night, and you want to do as well, at least as well in this scenario. Very classic scenario where you train in a certain geographic location, certain towns, a certain continent, and you want to run, of course, all over the planet. So very different cities in terms of traffic and cars and signs, etc. Maybe less obvious problem, but when you train on certain type of sensors, certain setups, like here, it's a classic camera, and then your actual camera is a fisheye camera. So this is a real scenario again. Or it's not the same resolution, so all the camera is not at the same height of the car. So you train on data which has a different angle. That's as simple as that, and it does change completely, or to some extent does change some aspects of your scene. Okay, and last but not least, this is the example that also connects to Tomas' talk, is you train on very sophisticated simulator, like the one which came out of video games, but they are still not quite the same as the real life. Okay, so imagine that typically that you have trained on synthetic images for the task that I mentioned before, which is semantic segmentation. So now you have a new synthetic scene coming in, and you do quite well. So this is the label for pavement, for street, for cars, etc. And then you take exactly the same neural network that you have trained for this task, which take an image as input and output as a classification label map, And this is the caption, and this is what you get. So you can see that there is, not surprisingly, if there is a substantial gap in distribution between train and test, you might face this catastrophic failure and drop in performance. So the idea of unsupervised domain adaptation is to address exactly this problem with some assumptions. The assumption is that at training time, you have data from both distributions, from the what is called the source domain and the target domain, but you only have somehow the annotation, the ground truth for the source data. Okay, so with synthetic images, it comes for free. I mean, you can generate, because you have modeled your scene, you have rendered your scene for free. You have the semantic label at each pixel, and because you don't have the time or you don't have the money, you cannot afford having human beings doing the same thing on your real images, which unfortunately are the one you care for. Okay, but you have these images already, or samples from your reality ahead of time. And the idea is to leverage this information to do as well as possible at runtime when you will see other images of this type. So this problem is fairly old, and there are plenty of literature not using deep learning, but I will just mention a few concepts here that is really especially effective with deep learning, and even in some cases which is very specific to deep learning. So the idea is that you need somehow to bring together these two distributions. You have to reduce or to fill in the gap between the two distributions of target domain and source domain. And you can do that at different levels. So if you remember some of the pictures you saw in the first talk with the convolutional neural networks, they take, in this case, images all the way to your output, and it means that it produces intermediate representations which are called feature maps of your raw data. So because of this long pipeline, which by the way gives the name of deep learning because it's many layers, you can try and bring reduce the distribution gap between your two distributions, either at the beginning of the pipeline or somewhere in the middle at the feature level, or even at the output level. Okay, and there are different tools to do that. And in particular, I'm going to mention these two here, which also connects to the previous talk. So you can use generative adversarial networks. So they were mentioned previously. So these are these kind of magic neural networks where you can produce incredibly plausible images of a certain type, like faces if you train on faces, or urban scenes if you train on urban scenes. And you can even use them to change the appearance of a scene from synthetic maybe to real, and vice versa, as we saw. So it's a very powerful, explicit way to bring the two distributions together. So you take the samples from the source distribution, your synthetic images, and you turn them into real. And because they are labeled in a sense, you end up with kind of real data, but with annotation, because they were originally synthetic and they came for free with annotation. So this is something powerful, kind of related, but in a different version. The way these generative adversarial networks are trained is called adversarial training, which means that the main neural network is trained jointly with another one, which is called the adversary, whose job is just to force the main one to do well. So if your main network is here to generate plausible urban scenes, the other guy, so it's another neural network, which is trained at the same time, is here to say, no, this is not a real image. So it has to classify, it's a classifier between a real or synthetic image. And by putting these two guys in competition, it forces the generator to do extremely well. And these are really incredible. It's a really incredible idea. And so discriminative learning means that you use an auxiliary discriminator to improve or to help doing something better. So in the case of domain adaptation, what you want to do is to make at somewhere in your main network, you want to make the data undistinguishable between the two domains. So you can have a discriminator trying to still differentiate between source domain data or target domain data. And one of the job of your main network is to accomplish your final task, and at the same time, at some point in the network, to make sure that these things become almost indistinguishable. And that's adversarial training. So I have, how much time do I have? Where is the timekeeper?
Yeah, you still have time.
Like, I can really
10
adapt.
minutes.
10 minutes, okay. So I'm going to skip this one. So I'm starting to trim my presentation. I want to bring this one because it's really just to exemplify this principle of adversarial training for domain adaptation. In this case, it's not for, so it's a paper from 15. It's for classification. It's not for semantic segmentation, although the examples I'm going to show about our work with not much detail is about semantic segmentation in particular. So in this case, it's classification. And here you have the, if you look at the just the top part, it's the sort of iconic representation of a classic deep learning pipeline, which goes from input images all the way to class labels. So you have as many output as you have classes, and you have to decide whether your image is likely to be a car image or a dog image, for instance. Okay. And so you have all these blocks where you have millions of parameters to be learned, and you learn that the classic way is to learn that through full supervision, where you give input-output examples, and you have to train such that at some point it does a good prediction on the training examples. So what you have here is an additional branch, which is the actual adversarial training part, which we'll see. I'm not, of course, not going to give the details and notations. Just look at the image here. This network here will be in charge of looking at these intermediate representation from the base architecture. So this is some feature, some abstract representation of the input, which is used later for the classification. And we try to decide whether these values for given inputs are from source data or target data. So it has to classify, and the game again is to make sure that the main the top part will eventually work in a way that for the images for which you have the annotation, it does a good prediction of the class. And for the others, or which you don't have, or for all of them for which you don't have, or you don't want to use the label, you want to make sure that the feature representation at this stage here has become indistinguishable between the two domains. Which means that later on, when you run your trained model on new data, which comes from the second distribution, we know that it will look like a target domain, a source domain data at some point in the network, such that the subsequent part of the network, which goes all the way to the decision, is not acted by the domain gap. So there are different different ideas that are the ways to implement that to do semantic segmentation. I'll skip that. This one, by the way, is using at the same time generative adversarial network, which is to translate. You see that your synthetic image is turned into something which is less synthetic in a sense, and at the same time use adversarial training. Just a remark on the complexity of such, and here I've hidden part of the architecture. For this type of architecture, where you use generative sort of a GAN to do a translation between the two domains and other things in between, each of these blocks here are different or partly different neural networks that you have to train. So it makes the whole architecture pretty cumbersome and not too trivial to learn. I think Thomas said already something about the adversarial training. So these are really conceptually really beautiful systems, and they do the job to some extent, but they are not trivial to train from scratch. Of course, if the model is provided by the author, it's another story. I'm going to skip this one, and I will finish in the coming in the last minute by so some of the contribution we did recently, just without equations, just the diagrams and a few results, qualitative results. So again, this is for semantic segmentation. So imagine that you have your synthetic scenes with, for free, the semantic segmentation, and you train your favorite architecture for semantic segmentation. So it's a convolutional neural network. And before the actual decision at each pixel, what you really have is, if you have here, imagine that you have 6 classes to be learned. For each pixel, effectively, you have 6 maps, which tells you for each class what is, for each pixel, what is the probability of being in this class, okay? So this is what is represented by this little stack of maps, okay? So now, so you have trained that. Here I'm going to show without adaptation and then with adaptation. So if you train this guy and then you run on a new synthetic image of the same data set or coming from the same game engine, well, you will again, this is the example you saw before, you have a decent segmentation map. And of course, if you on the target, an image from the target data, you get this. And one thing which is interesting is that if we look not, so this is the final decision. It shows for each pixel what is the most likely class among all the classes. But if you look at what is just before, which is this stack of as many maps as you have classes in your dictionary, and if you look at how dispersed are the prediction for a given pixel, so for the people who know these things, it can be captured by the entropy. So you essentially you compute for each, you can measure for each pixel how confused is the network, or how confused or non-confused is the decision. It doesn't mean that the network is right. It means that it is confident or not, okay? One can be wrong and being very confident, and it's very true for neural networks. So what you see here is that if on the image which come from the source distribution, the network is fairly confident everywhere except for well, the boundary of the objects, which is not surprising. So so this is the classic heat map where the colder the color, the lower the uncertainty in this case, and the warmer the color, the opposite. And if we look at the same quantities on the other case, this is what you get. So you see a lot more of warm colors, so a lot of confusion in the decision, and also a lot of, if you look spatially now, if you look at the structure of this image, which is the entropy, it's very noisy. And the idea is really to leverage, to try, let me rewind. The idea is to reduce the gap between these two guys in terms of statistics of these two maps. And this is what we have proposed by enforcing explicitly for the target data for which you don't have the ground truth segmentation map, but for which you can compute these quantities given your segmenter, to enforce explicitly that this entropy becomes more like the other one, okay, using an adversarial training and different tricks that I'm not going to explain. What is it? Yeah, and this is essentially the rationale. So this is a work that we're going to present in June at CBPR. And again, the idea is to, at training time, to make sure that the network will output, even on target data, target domain data, prediction which are more confident and less noisy, and which essentially resemble more to what you would get on source data domain. Okay, and hopefully this is what you would get. So much less, okay, so you see that here we have sort of reached the goal, which is they really look like a similar entropy map, and it does translate into a way better in this case. It's not always that better, but in this case, way better semantic segmentation. So to show, I'm going to skip all this, and so these are examples of qualitative example on this scenario where the training set is for the people playing with that is I think is Cynthia here. So it's synthetic images, and the test or the target domain is real images from cityscapes, for which, by the way, we do have the ground truth, but we pretend not to. But we use it for evaluation. And this is what you basically look at here and there. So this is what you already saw. This is without adaptation, and this is the ground truth, and this is with adaptation according to what we propose. But probably better to see the video. Last time I tried to play the video, it just killed PowerPoint, and I think it just did. Okay. It just did. So Mathieu is the second time that you see this embarrassing moment. Where I have to kill PowerPoint. It's just terrible. Yep. But I think it's good to see the video also, to see to get a feel of the improvement that we get. Okay. Let's see, crossing fingers now. Where is it? Yeah. Okay. So you see now a full video. So this is without adaptation, with adaptation, and these are the this little image are the entropy maps. So I will going to. So you see that so far it's way better, but at some point it's interesting to see that we don't completely recover from this very annoying kind of situation where the pavement label is bleeding into the road because of the pedestrians, which tells a lot about. Again, how far we are in terms of holistic understanding of a scene with neural networks. So we've done progress, but there is still a lot. But what is really important is to see that in this proposal, in this work, without so the main architecture, which is the semantic segmentation, is not changed. I mean, you take one, your favorite, and you have this just additional module, which are at training time, assuming that you have target domain data without any label, you can improve to some extent, and we have measured to which extent we've improved the performance. And I will finish with one example, and I will skip the one example on another task. So there are, in visual perception for self-driving cars, there are two sort of two critical tasks. One is semantic segmentation, not to that granularity, but at least for street and drivable space and pavement. And the other one is obviously object detection. So object detection introduces essentially to have a bounding box around pedestrians, cars, vans, etc. And in this little example, I show you it's a very sort of academic or toy example where we train on cityscapes. In that case, it's real data for which you have this annotation of objects, and we want to see how it looks, how much we gain by annotation if we were to the same time we were to run the detector in foggy scenes. As it turns out, this dataset cityscapes has been turned by a team in Zurich into a foggy version. So the fog is synthetic. Actually, in this version, it's not so good. It's quite visible. But because there is the depth information in this scene, you can synthesize a fairly okay-ish fog with different density depending on the depth or the distance to the physical points. And just to show you that if you train your detector without the fog and then you run on the foggy scene, this is what you get. And not surprisingly, you have a number of misdetection. And with the proposed adaptation, you recover most of these misdetections, which is obviously quite important. So which brings me to the conclusion. So domain adaptation and transfer learning at large is really important for people doing deep learning or reinforcement learning for real life problems. And in order to move forward, there are many venues for future research. One which is especially important for the thing we do at Valeo.ai, because Valeo is building different sensors and is trying to leverage as much as possible these sensors, is really to make use of different inputs. Clearly, the domain gap in the visual domain in images might be less large if you look at the LiDAR points, for instance, between synthetic and real data, for instance. So this is something that we really want to investigate now. And with this, I conclude my presentation, and I thank you very much for your attention.
Are there any questions?
Have you tried with regards to the driving environment? Because that video looked like somewhere in Europe. For example, conditions that would be elsewhere, for example, Middle East, Asia, or North America, if the process would be the same?
So we haven't tried, but it's clearly one of the interesting use cases for this type of scenarios. So in this paper, we have compared on certain benchmarks. We have for which we can compare to other research teams, which is what is called the synthetic to real. It's one classic scenario. The other one is the one you mentioned, which is across cities. We haven't, we don't have the numbers on this one, but it's definitely something that we should do. We don't, I mean, there is no reason for, I mean, I don't know whether we will beat the state of the art or this one as we do on the synthetic to real, but the approach itself has no reason to be changed at all. It's just that now your source domain is European towns, as you said, and target domain is, say, Asian towns, and there are actually benchmarks for that. So it's well, thank you for reminding me that it's on our to-do list. But no, that's a very good comment, and it's a really real case scenario we have at Valeo. We have the self-driving car, which is developed between Germany and Paris, and then it is replicated in Japan and in San Francisco. And as you might expect, you need some fine-tuning, and not necessarily because of the different side of the road where you drive, but for Japan, it seems it's because of very differently looking cars. Some of the cars which are very box-like, that you have a lot in Japan, they're very well detected by the thing that was the system which was trained in Europe. So that's a very important problem to address.
In the adaptive process, so you go from real to virtual, as I understand, but you use also photometric dimension in order to make this closer. Like you don't show exactly how you reprocess the image.
In our case, we don't. I showed one example where there is an explicit, what is called translation of images from one domain to another, which is basically from source to target. So you have your annotated data, and because you know how the target data looks like, you force by this translation to make your source data for which you have the ground truth to look like as much as possible the raw data to the target ones. So this is one approach. We don't do that, or said differently, we do it, but not at all at the input of the network, but almost at the very end, just before the decision. And when you think of it, it's probably easier to align things at the end than at the beginning. So as much as image translation or with cycle GANs is powerful, it's still, I mean, it's quite an overkill to try. In a sense, we don't, I mean, what matters is the final decision, right? So for visual effects, it's fantastic, by the way, to do cycle GANs. So we don't do it, but some other people do, and yeah, and we found that as per now, what we get works better, but it's by, I mean, the state of the art changes every month or at every conference, so one has to stay tuned. But it's very powerful. I think one of the key messages is that the same idea of bringing things together can be seen at the beginning or somewhere in the future presentation or at the very end of the network, and yeah.
So you tried and you compared your results.
Yeah. I skipped the dry tables with figures, but the reason for doing on benchmarks is that we can really compare to the competition. and you try to beat by a few points, which is not easy. But we have metrics for that. As when people do validation, and in Valeo in Prague, there is a lot of activity, as we saw again today, on validation. Well, when you have to prove to some extent that your system is doing better than your previous version, or you need metrics, and this is also what we have to compare state-of-the-art methods.
Yeah, but just one thing to add something about this kind of system could be very interesting in an unsupervised way, because you can really transfer that data from one domain to another. But here we are talking about supervised things. So the idea of this kind of systems, they transfer the data, and then after they consider that the labels are the same. And actually, that's why it doesn't work so well. I mean, this kind of techniques that try to transfer from the raw data. To transfer the raw data straight away, because they consider then that the labels are the same, and usually it's wrong. Because in your target data, I mean, when you transfer, I mean, when you do this kind of transfer from the raw data, you are going to move structure, to move the car, or things like that. So their shapes are changing.
Yeah.
And in the supervised framework that they consider, the labels are not changing. And so somehow, I mean, they really degrade the supervised framework that they have. And the supervision, of course, is very important. That's why actually when you try to align most on feature, you get rid of this problem.
I'd like to ask you if you are using now or planning to use information about dynamics in the scene. Let's say that in this video, if you would know that the images are somehow continuous, then and you are certain in some areas that this is road, this is pavement, then changing.
Well, we don't at the moment. If we plan, maybe, but it's obviously something very important. So there are two aspects. One is the mere temporal continuity or consistency that we could easily enforce in complement to what we do. There is something probably something a bit more powerful, which is really to learn about dynamics. In that case, meaning that some class of objects evolve in a certain way, some other class in different ways. Some objects are rigid, some objects are not, etc. And you might as well put that into a training framework. But then we are back to the annotation hell. 5,000 images in cityscapes. They're obviously not contiguous images in videos. Otherwise, you just have a very short video. So they're all completely different. So having this level of annotation at the pixel level on all the frames of many different diverse video, apart from doing that with cinematic images, which we can do, is difficult. But then, again, the gap here was essentially visual, but then you have also the dynamical gap in your virtual world. Does the car, we just saw that as well with the robots, how much the dynamics of the car and even more the dynamics of the other objects in your scene look like. I can tell you, if you look at Carla, all these the state-of-the-art simulator for this type of urban scenes, I mean, it's still like video games. Okay, it's not quite what you see in the streets of Paris or Prague. But I mean, it's definitely something to look at, and but it's not something that is not which is right now on the agenda, but it should be soon enough.
I would like to ask, you presented the filling of the domain gap between simulated data and real data, and you also mentioned that you consider this as an approach for filling the domain gap between world sensed by different sensors.
Yeah.
And my question is if you basically tried to perform this transfer learning between different sensors. For example, it would be interesting for me how it would fill the domain gap between a classical camera and this fisheye camera. For me, naturally, fisheye camera will have larger like uncertainty on the edges because this is basically the optics. But this approach will force it to be certain on also on like the edges of the field of view, which would be wrong. But
Sure. I mean,
I would like to know if you played around with these.
so we haven't played in a scenario where you go from a narrow field camera to wide angle. In that case, the geometry distortion is quite severe. But as it turns out, and the other colleagues actually in Tube in Ireland and I've worked on this, and they show that even training in that case for object detection, for semantic segmentation, it wasn't so bad actually. Not to try, you learn on cityscapes, which is really a classic narrow field of view camera, and you just run on the fisheye because probably locally it's enough. Although one might argue that you destroy completely the stationarity, which is at stake in a convolutional neural network. So it was kind of surprise to me. For detection, it's another story. But this is just out of the oven, just recent research. So we haven't tried, but now we can all the possible scenarios. But now we are really actively looking at how to apply it to actual use case that we have in Valeo. It's really like you take it from the shelf or the desk of the researchers and you have it on the data people have in production. So it requires some work, but it's something which is of course of interest for us. But when you, in that case, you can also, there are ways to align images. I mean, you can undistort the geometry. I mean, there are. I wouldn't like to give the impression that everything has to be done only with by training, by brute force learning, etc. There are sometimes some simple things to be done, which at least as baseline. So you take your fisheye camera and you unwrap it into something. There are different ways to do that, but it's something which almost look like a classic camera, and it's already a good baseline. But yeah, to be seen. But I mean, the answer about the uncertainty, you're right. First of all, the entropy principle that I showed is interesting. Is not the end of the story, and by enforcing low entropy in the decision, we might end up with a network which is wrong but confident. Yeah, that's a risk. But so far, it was way more beneficial than not. But it could be in this case. To be seen.
Some more questions? If not, then thank you very much for coming today, and hopefully see you next time. I really enjoyed the presentations of today, and I enjoyed as well how it was kind of linked to the previous meetup. The last one that was related to the game development and the use of game development in autonomous driving. And you could see as well Vincent Zimmerman, who was one of the speakers in our last meetup, even though at the moment he was just overrun by the robot there. But still, thank you very much for coming, and see you perhaps next time.